So, have you ever wondered what goes into designing an experimental plane, such as the HyperX? I know I have. I'm here at NASA Langley Research Center in Hampton, Virginia, to talk to Dr. Scott Hum.
What are the steps in designing an aircraft?
How does the mission requirements of an aircraft determine its shape?
Why are wind tunnels important in testing aircraft designs? Why?
Hi, Dan.
Hey.
HyperX is definitely a very exciting program. In my job, I use wind tunnels to determine the flying characteristics of a variety of different vehicles that fly many times faster than the speed of sound, like the HyperX. Here, the exciting part of the HyperX program is that it's truly pioneering. That means no one's ever done it before, so we have to blaze the trail.
NASA sure has blazed many trails. How do they do it?
The first thing you have to do when blazing a trail is to determine a mission, or where you want to go. We develop a set of requirements for the vehicle, and then we begin a process of designing a vehicle to meet that mission. Have you ever been to an air show to see a bunch of different airplanes?
Yeah, some planes are short, some are long and slender, some fly slow, and some fly fast.
You're right. They look and perform differently because they were designed to satisfy different missions. For the HyperX program, our mission is to have it fly very fast. We also want to be able to control it, and we want it to be able to propel itself. You see, NASA has many years of experience testing fundamental shapes to understand and document how those shapes, we call them geometries, respond to the airflow at various speeds. Let me show you. The Apollo capsules used to bring the astronauts back to Earth after their trips to the moon were designed as blunt bodies. This is because this particular shape has high drag, a force that slows an object down.
The blunt body creates the drag needed to deploy the drogue parachute, followed by the main parachutes. The force of drag then gently lowers the vehicle safely to the Earth.
NASA had to design a vehicle that would slow down to speeds where it was safe to deploy the parachute for landing in the ocean.
Okay, I get it. But what about other shapes?
Well, we know that slender shapes, like the Concorde, have less drag. A vehicle that has to propel itself, like the Concorde or the HyperX, has to have an engine with enough power to overcome the vehicle's drag. So if you were designing the HyperX to propel itself and fly really fast, would you want a blunt body or a slender body?
I'd want a slender body.
That's right. The HyperX is designed as a slender body because it has less drag for the engine to overcome. You're well on your way to becoming a conceptual designer, Dan.
I am? Sweet. So, once you've decided on a mission, what's next?
Detailed design. A conceptual designer makes decisions like the one you just made to find a geometry that will meet the mission requirements. The detailed designer uses tools such as CAD or computer-aided drafting to turn ideas into drawings. These drawings help us work out the details of how to design parts of the HyperX, like the engines, the control surfaces, the fuel tanks, and so forth. Once we have an initial design, we begin a process to improve it. We compare the design of the HyperX to other vehicles with similar characteristics. We may need to make changes to the geometry to improve the performance.
How do you know if you need to change the shape?
One way is conducting wind tunnel tests. You see, during the design and computer modeling stages, we extensively used our wind tunnels to quickly screen our HyperX designs. And then, the wind tunnel tests helped us to determine the best design and to understand how the vehicle will fly.
Okay, so what is a wind tunnel?
Wind tunnels are devices that allow us to move air over a scale model of a flight vehicle, like the HyperX. We use models instead of the real vehicle because they're smaller, less expensive, and easier to change if needed. This is NASA Langley's 31-inch Mach 10 wind tunnel. This tunnel can get the air moving up to 10 times the speed of sound. Once we place the model of the HyperX in the wind tunnel, we make measurements to determine how the air interacts with the model. At the nose of the vehicle, the flow near the surface is very smooth. We call it laminar. But as the air moves down the length of the body, it changes and becomes turbulent. You can see this natural process by looking at the smoke after you blow out a candle. After you've blown out a candle, you'll notice that the smoke near the candle rises smoothly. That's laminar flow. But farther away from the candle, you'll notice it becomes rough and irregular. That's turbulent flow. Normally, we think of laminar flow when designing aerodynamic shapes. We want the air to flow smoothly around them. However, for the HyperX geometry, we require turbulent flow.
Why would you want turbulent flow on the HyperX?
In order for the scramjet engine to work properly. You see, turbulent airflow enhances the mixing of the air with the hydrogen fuel for better engine performance. Turbulent airflow is created by a device called a trip located underneath the belly of the HyperX. Using the wind tunnel, we tested several trips with different shapes or geometries to see which one worked best to change the airflow from laminar to turbulent. Our wind tunnel test determined that this triangular-shaped trip was the best design for creating turbulent flow for the scramjet engine on this vehicle.
How do you test the scramjet engine?
We have specialized wind tunnels capable of testing scramjets, but the ultimate proof of the HyperX is flight testing. That's the last phase in designing an aircraft. NASA conducts all of its flight tests on aircraft at the NASA Dryden Flight Research Center in Edwards, California.
Thanks, Scott. We'll visit NASA Dryden Flight Research Center later in the show. But first, join me in Dan's domain, where we'll use technology to prepare for today's math-based, hands-on activity.